Hello everyone, welcome to MES e-learning channel. In today's video, we will be discussing Routh's stability criterion. So let's look here. So we know that this axis is called as the x-axis and this is the y-axis. This is the real axis and y is the imaginary axis. We will be denoting the real axis with sigma and the imaginary axis with j omega, right. We are aware that this is the positive side of the axis and this is the negative side of the axis, right. We know that a transfer function will have poles and zeros. It will indicate the system's poles and zeros, and that is nothing but the roots, right. So, roots are nothing but a combination of poles and zeros, right. So, we will be using Routh's stability criterion to identify whether a given system is stable, unstable or marginally stable. Now, how do we do that? We will see. Okay. So, before that, let us understand when do we call a system is stable, it is unstable or marginally stable. So, if the roots, meaning the poles and zeros, if they lie on the positive side of the S plane. Now, what is the S plane? This is nothing but the S plane. Okay. So, if the roots lie on the positive side of the S plane, that is here, then the system is said to be unstable. Okay. So, if it is on the positive side, then it is unstable. Similarly, if the roots lie on the negative side of the S plane, meaning this side, right, then it is said to be stable. And if the roots are on the imaginary axis, meaning here, right, on the imaginary axis, then the system is said to be marginally stable. Okay. So, let us quickly revise this. So, if the roots are on the positive side, they are said to be, the system is said to be unstable. If the roots are on the negative side, the system is said to be stable, and if the roots are on the imaginary axis, the system is said to be marginally stable. Okay. Now, let us go ahead and find out if, how do we identify if the roots are on the positive side or on the negative side or on the imaginary axis. So, let us solve a small example to understand the topic better. So, here we have the transfer function as written on the screen. So, while solving Routh's stability criterion numericals, we are interested in the characteristic equation. In the question, you will be directly given the characteristic equation. Okay, you will be given a characteristic equation. If not, you will be given a transfer function from where you can take the denominator, which is nothing but the characteristic equation. Okay. So, this is the equation that we have, and this denotes the characteristic equation. Okay. Now, let us go ahead and try to solve this. So, as I told you, this is the characteristic equation which we will be using. So, to solve the Routh's stability criterion numericals, first thing that we need to do is we need to form Routh's array. Okay. So, we will have to form Routh's array, and how do we do it? Okay. So, we have to basically look at the question that is being given to us. Okay. We have to look at the characteristic equation that we have at hand, and then we need to write these terms on the left side, okay, which will form a column. Okay. So, here you see we have the highest power of s here is s cube. So, starting from s cube, we go on decrementing the power, okay, and we go on writing it one below the other. So, we have s raised to 3, s raised to 2, then we have s raised to 1 over here, and here there is no s. So, we can write s raised to 0 because anything raised to 0 is 1, okay. So, s raised to 0 is going to be nothing but 1. So, if we assume there is 1 over here, we can simply write s0. Okay. Now, with the help of the characteristic equation that we have, we can fill these two rows. For s raised to 3 and for s raised to 2, we can fill in the rows. Now, how do we do that? Here with s cube, we have the number 3 if you see. So, we will write 3. Okay. Then with s raised to 2, we have 4. So, we will write it in front of s raised to 2. Okay. Along with 3, what we are going to do, since here we have odd power, all the numbers that are along with odd power of s, we will be writing in this particular row. In this particular row, we will be writing all the numbers that are with a term s which has an even power, okay, which has an even power. Okay. So, we have the characteristic equation, I will write it here. So, as I told you, okay, numbers which have s that has an odd power will be in this particular row. So, we have 3, then we have 2, okay, and then here we have 4 even powers of s, and here this is s raised to 0. So, this 3. So, with the help of the characteristic equation, we have filled the first two rows. Now, we will have to fill the remaining rows as well. So, to do that, how are we going to do it? We basically have to cross multiply, okay, few numbers. How do we do it? We will have to look at the preceding row. What does preceding mean? Just above of what we are looking for. So, we are looking for s raised to 1, right. So, we will have to look just above, okay, the preceding rows. So, the preceding rows have what? They have 3 and 4, okay, and along with it we have to take these two numbers, that is 2 and 3. For which position we have to find the value of this position. So, for that we will have these two numbers that are immediately preceding above that spot and the two values that are beside it. Okay. Now, what we will do? We will be doing cross multiplication. So, please keep in mind we start from this number always, okay, which is just above the position that we are looking for. So, 4 is multiplied with 2, okay, 4 is multiplied with 2. So, we have 4 into 2 minus 3 into 3. We will have minus in the middle, please keep in mind, and s is divided by this number only, that is the 4. Okay. So, if you solve this, you will get 8 minus 9 upon 4, which is nothing but minus 1 by 4, which you can also write as minus 0.25. Okay. So, we will write this value over here, that is minus 0.25. Okay. And for this position, again what we will be doing? We will be using these two values only for the cross multiplication, and since we have already used this, we will not be using this, we will be moving ahead here. But here if you see, there are no numbers in the array. So, here we can simply write 0 because we do not have any values to cross multiply, or rather we can say there is nothing, means there is 0 over there. If we cross multiply also by multiplying with 0, it will ultimately result into a 0. So, we will simply write it as 0. Now, we will solve for S0. Like I told you, we will see the preceding two rows just above S0. So, here now we have 4 which we will have, and we will take this value, right. So, we will write here 4, then we have minus 0.25. Then for this position, we will take the set of these 4 numbers. So, we have 3 and 0. Now, again we will be cross multiplying, always starting with this number which is just preceding, and then we will cross multiply, we will get minus 0.25 into 3 minus 4 into 0, which is nothing but 0, correct, divided by always this number minus 0.25. So, if you solve this, you will get, so this will get cancelled and you will get 3 as answer. So, you can write 3 over here. Okay. So, we have completely filled the Routh's array. Once you have the complete Routh's array, you have to look at the values in the first column of the Routh's array. Okay. So, here we have, what all values do we have? We have 3, we have 4, then we have minus 0.25 and 3, right. So, we have to see if there is a sign change in the first column, right. So, here this is a positive number, this is a positive number, this is positive, then this is negative, right. Over here you can see, and this is also positive. So, this is positive, again the next number is positive, so there is no sign change, but here from positive the sign has changed to negative. So, yes, there is one sign change over here, then this negative sign has then changed to a positive sign. So, again there is a sign change. So, there are a total of 2 sign changes, okay, that are happening in the first column. So, the number of sign changes is equal to the number of roots that are present on the right side of the S plane. Okay. So, the number of sign changes is equal to the number of roots present on the right side of the S plane. Okay. So, there are 2 sign changes, right. Hence, there are 2 roots, okay, 2 roots on the right side of the S plane, and since there are 2 roots on the right side of the S plane, that is the positive side of the S plane, hence we can say that the system is unstable. Okay. I hope you have understood. If you have any doubts, please write them down in the comment section. Thanks for watching.